Welcome to another video of chemistry revision. Today we're going to be revising paper 1 topic, bonding and structure of different compounds and everything and their properties of matter. This is really the backbone of chemistry. This is what you really have to understand and be able to apply to compounds that you have never seen before in your life if you want to get that high grade in chemistry. So it's longer than usual because I explain it really thoroughly, because there's a lot of really important and potentially complicated topics to understand in this video. So please subscribe if you find this helpful, and I hope this increases your understanding of chemistry, because this really is a core part of what it is. Now we're going to go and look at what's been taken out of everyone's courses. So first of all, it's important to note that pretty much all of the content in this video will appear in your exams at some point. None of it has been taken out completely, but you will have a major focus to focus your revision on. So if you're doing combined science foundation, then you really want to focus on how the structure of the compounds that we talk about are related. So this includes the states of matter and ionic compounds and covalent compounds that we talk about, as well as the properties of metal, and then the carbon allotropes as well. For combined science higher, it's exactly the same thing, but do remember the ionic and covalent bonding is still going to come up. You're still going to see it. It just isn't going to be a major focus of one of the questions. So if you're taking chemistry as a separate science, or what I call a triple science, and you're on the foundation paper, then your major focuses for this video are the actual bonds themselves, the properties of the substances formed by those bonds, as well as nanoparticles. That's the key thing. Your exam's the only one that's going to contain nanoparticles. And for triple science higher, you've got the bonds, you've got the structure of the bonds, you've got the carbon allotropes all as your major focus. So everything in this video is going to be your major focus, but taken out completely is nanoparticles. So you don't have to worry about nanoparticles. That's the only bit of your paper that you don't have to worry about. There's no required practicals covered in this topic because there aren't any. So with that, we're going to start the video. So let's get cracking. We're going to go through these nice and slowly so that you understand everything, all the concepts behind them, and so that by the end of the video you're going to be able to apply all of this knowledge to unknown compounds, and you're going to ace your exam. So pause the video and have a go at these first 13. So to start off with, the 3 types of bonding are covalent bonding, ionic bonding, and metallic bonding. Covalent bonding happens between 2 non-metals. Ionic bonding happens between a non-metal and a metal, and metallic bonding happens between 2 metals. Before we go any further, I want to mention the key point for this video that I mentioned in the previous video, which you should definitely go and watch, is that elements and compounds atoms react and bond to get a full outer electron shell. That is what they want. So that is how each atom is going to be bonding, so that they can get their full outer shell. So in covalent bonding, that's where 2 nonmetals, they share electrons. They have a shared pair of electrons, maybe multiple. We'll look at that in a minute. In metallic bonding, the metal atoms lose the electrons on their outer shell to form a web of positive metal ions, and then there's this sea of delocalized electrons. Again, we're going to go over this in more detail in a minute. And in ionic bonding, the metal gives its outer electron to the non-metal. So if you remember back from the previous video, we talked about how metals often have 1 or 2 electrons on their outer shell, whereas non-metals usually have 6 or 7. That's group 1 and 2 and 6 and 7. So the metal gives away its outer electrons to the non-metal, The metal forms a positive ion because that's what a metal is. The non-metal forms a negative ion because that's the definition of a non-metal. It doesn't form a positive ion, and they bond together because positives and negatives attract. Things that bond ionically form ionic compounds. Things that bond metallically, well, they just form metals, and things that bond covalently could form a variety of things, which we're going to look at in a minute. So, what happens in ionic bonding? Well, as I just talked about, the metal atom gives its outer electrons to the non-metal atom. So the metal atom forms a positive ion, the non-metal forms a negative ion, and because the opposites attract due to the electrostatic forces, they all come together in a regular lattice formation to form an ionic compound. And all the atoms have a full outer electron shell, so they're happy. So this is what we call a dot and cross diagram. We show the element using the chemical symbol in the middle, and then it also shows the outer electron shell of the element. So sodium has 1 electron out in its outer shell because it's in group 1. Chlorine has 7 electrons on its outer shell because it's in group 2. Generally, we often use a dot to represent one element's electrons and the cross to represent the other, just so we don't get confused about which electrons come from which element. So how we show that these two have been ionically bonded is we show that sodium has lost that electron, so now that electron shell is empty, and chlorine has gained this electron to make this full outer shell. It's formed sodium chloride, and the key thing with dot and cross diagrams for ionic bonding is you put the square brackets around it and show the positive and negative charges. Obviously sodium, because it's a metal, has formed a positive charge, and chlorine is non-metal, so it's formed a negative charge. So sodium chloride is a nice easy ionic compound to form because this 1 electron from the sodium fits nicely into the 1 electron gap in the chlorine's outer shell. But what if we get something like the ionic bonding of magnesium here and bromine here, where magnesium has 2 electrons to lose, but bromine only has 1 gap. So what we need is we actually need 2 bromine molecules so that we can fit 1 magnesium in each, and obviously this will form an ionic compound where for each 1 magnesium atom there's 2 bromine atoms, and magnesium bromide would be its name. Note that magnesium forms a 2+ ion, whereas these have 1s, but you can just write minus. Why is this 2+? Well, if you remember, these are positive because the electrons are negatively charged while the protons are positively charged. Normal atoms have the same number of protons and electrons and therefore have no charge. But when we start losing and gaining electrons, we get ions, and these have a charge because, let's take magnesium. Magnesium now has less electrons than it does protons, so the positive charge of the protons outweighs the negative charge of the electrons by 2. So we symbolize that 2+. This is a magnesium 2+ ion, and we have 2 bromine minus ions. It's worth noting that in a simple equation, this is how we would write magnesium bromide, this ionic compound, because we have 1 magnesium and 2 bromines, so it would be MgBr2. And this is what we call an empirical formula. So it's essentially just what you see in the chemical equations, remember. It's nothing too complicated, but you are expected to be able to work out how many of each atom will appear, so whether this bromine will be 2 or 1, or whether this will be 2 or 1, based off how the atoms ionically bond, based off which group they're in, because remember, if they're in group 1, they're going to have 1 electron on their outer shell. If they're in group 6, for example, they're going to have 6, and it's that pattern. If you've watched the last video, you're going to be familiar with that. You have a periodic table in your exam, so you are able to tell. So question 4 here is simply practicing what I just discussed, the empirical formula, this time of potassium oxide. So we have our metal potassium and non-metal oxygen. Remember, you will be given random compounds in your exam, you'll have whole questions on them. You've got to identify which parts are metals and which parts are non-metals, so that you can work out if they're ionically bonded, covalently bonded, metallically bonded. Then you can work out their properties, and that's most likely what the questions are going to ask you. So potassium is a metal, oxygen is a non-metal. So how are they going to fit together? We're going to look at what group they're in. Potassium is in group 1, so it has 1 electron in its outer shell. Oxygen is in group 6, so it has 6 electrons in its outer shell and 2 gaps. So it doesn't fit together perfectly. So what we need is we need 2 potassiums so that we can get 2 electrons to fill oxygen's outer electron shell. So this would be its empirical formula, because you have 2K, 2 potassium, and 1 oxygen. Remember, if you're not sure about the chemical symbol, just look at your periodic table. So you could draw a dot and cross diagram for potassium oxide bonding if you wanted to, if you felt you needed more practice with that. So, what is an ionic compound? Well, ionic metals and non-metals bond ionically to form ionic compounds, and they're just giant structures of ions, remember, in that regular lattice formation. So if you remember, I talked about that because they're of opposing charge, the positive, say, potassium, and the negative, oxygen, these opposite charges are going to attract and hold them together, and these bonds that hold these atoms together are strong, and we call these electrostatic forces of attraction between the positive metal and the negative non-metal. And these forces act in all directions in the lattice formation, and that's what an ionic compound is. Remember, ionic compounds, pretty much all ionic compounds are salts. That's important to remember, because we're going to talk about salts later on. If you imagine a salt, it's salt crystals, for example. You can kind of see how they're square and they're cut. That's because that ionic compound structure isn't going to cut like nice and curvy like other molecules might, because it's all bonded together. You're going to get it all jagged and yeah, like that. So here we are back in Paint, this time looking at a ball and stick diagram to represent an ionic compound. I could have probably done a better drawing, but I've got time restrictions, so this is all you're getting. So remember, this shows the sodium atom, the positive ion, sorry, it's not an atom, it's an ion, and the negative chlorine ion. Remember, the chlorines and sodiums are going to be opposite, because each sodium is only attracted by the electrostatic forces of attraction to the chlorine ions. And you can see I've extended all these lines. I should probably have extended these lines up as well. This just shows that this is only a small part of it. You know, this kind of structure, this regular lattice structure, extends out as large as the salt, as large as the ionic compound actually is. So here is how we represent ionic compounds in 3D. This is a 3D model of a sodium chloride crystal. Obviously we have the sodium ions in purple here, and the chloride ions in teal. You may note the sodiums aren't touching each other, and the chloride ions aren't touching each other either. That's because you've really got to remember this. It's only the positive and negative ions that are bonded and attracted together. So there's no actual attraction between 2 sodium ions or 2 chlorine ions. The attraction is only between the opposites, because it's electrostatic. The specification does say that you need to be aware of the limitation of using these models to represent ionic compounds. So the limitations are basically just the problems, what's inaccurate about our models, because scientists are very fussy about being accurate, as you may have gathered by now. So this is obviously the dot and cross model. They're good for showing how the ionic compounds are formed. However, they don't show like the size of the ions, for example, and how like they're arranged in their formation. So magnesium bromide obviously would be arranged slightly differently to sodium chloride, because you have 2 bromine ions to every 1 magnesium ion, so they would be arranged differently, but dot and cross diagrams don't show that. and it doesn't really show the structure either. It just shows the individual, want to call them atoms. Before they're bonded, they're atoms, but after they're bonded, because they have charge, we call them ions. The limitations of our lovely ball and stick model here is simply that it isn't to scale, and also there aren't gaps between the ions like this. They're more like the 3D model. They're all packed together in that lattice formation. There's no gaps. But the ball and stick model wants to show the bonds as well, but that's kind of inaccurate, or it's a limitation from a scientist's point of view. And finally, this 3D model is it's pretty accurate because look, it shows the scale and it shows the structure of the ionic compound. However, you can only see the outer layer of the compound. You can't see inside and how the pattern continues inside. So that would be the limitation of this 3D model. And the final thing to study about ionic compounds, do they have high or low melting and boiling points? This is very important to learn for all of the products of bonding, their properties, so melting and boiling points, and their relation to how the bonds, because obviously as we melt and boil compounds, the bonds between them are broken, weakened as they melt, and then broken completely so that they can fly around as gases. We look at this more in physics, and we're going to look at it a bit more later as well. But ionic compounds have high melting points, very high melting points, because those strong electrostatic forces of attraction that are holding the ions together in their tight lattice formation make it nearly impossible to separate them. You have to have really, really high heats to start to weaken those bonds between the ions and allow them to form into a liquid and a gas, you know, even higher temperature, boiling point. And ionic compounds as a solid do not conduct electricity. However, when we dissolve ionic compounds in water, because some do dissolve in water, or when we melt them at really high temperatures and put them into their molten state when we melt them, the ions, obviously the individual, the ions, they're like the sodium ions and the chlorine ions, for example, they're free to move, and this allows them to carry electric charge, which is basically how electricity moves, so they can conduct electricity. I don't think you're going to need to know much more than that about how electricity functions. I don't know, maybe we go into it a bit more in physics, I'm not sure, but for now that's all you really need to worry about. They conduct electricity when they're dissolved in water or they're melted in their molten state. So, well done, you made it through everything ionic bonding related, and I know there's a lot to take in there, but unfortunately there is yet more. We have covalent bonding, a whole new world of non-metals sharing electrons. So if you want to pause the video and have a go at these 19 questions. So, what is a covalent bond? You need to remember this definition. A covalent bond is a shared pair of electrons. Remember, don't just say it's where two non-metals share electrons. It's a shared pair of electrons. You need that word pair. It's going to get you an extra mark in your exam. So, covalent bonds are strong because you have those electrons being shared between the non-metals. So, each atom has, basically each atom has 8 electrons now in its outer shell by sharing them, by coming together, and not transferring them like ionic bonding, but like sharing, coming together and sharing. And again, the electrostatic forces of attraction between the atoms as they come together to share those electrons mean that covalent bonds are very, very strong. So I thought we'd do a quick link back to something we covered in the last video, how group 7 are diatomic, because as you can see they go around in pairs so that they can have their full outer shell, because this chlorine has 7, this chlorine has 7 because they're in group 7, they have 7 electrons on their outer shell, and this is a covalent bond, this shared pair of electrons, meaning that each chlorine can benefit from a full outer shell. They're diatomic. And this is a a dot and cross diagram for covalent bonding. It's also worth remembering things like oxygen, nitrogen group 6, they're diatomic as well, whereas the noble gases, as we covered, are monatomic. They go around on their own because they don't need to be covalent bonded because they already have a full outer electron shell. So here is your covalently bonded water molecule, because obviously H2O, so you've got two H's and one O, oxygen group 6, so you have the 6 oxygen electrons and the one hydrogen electron, because hydrogen has one electron because it has one proton. So you can see it's made two covalent bonds. There's two shared pairs of electrons, and you need to be able to draw simple covalent molecules like this by knowing how many electrons they have in their outer shell, and therefore you can figure out how many covalent bonds they're going to make with other molecules. I should add that there are specific covalent molecules on the specification that you need to know. Most of them are simple, like oxygen O2, chlorine, Cl2, chlorine I just showed you. The four most complicated I've chosen for this PowerPoint. We got hydrogen, chloride, ammonia, methane, and water. So I'm going to show you how all of those would generally covalently bond. Obviously, water's H2O, ammonia is NH3 nitrogen with 3 hydrogens, methane is CH4 carbon with 4 hydrogens, and hydrogen chloride is HCl, 1 hydrogen, 1 chlorine. So this is the displayed formula for ammonia NH3. We do have to do more displayed formulas when we look at organic chemistry in paper 2, but we basically just we put each atom here, and the lines show the covalent bonds. Obviously each would be a shared pair of electrons. I should quickly add that, in case you're wondering, because hydrogen only has one electron, the first electron shell only fits 2 electrons, so hydrogen reacts to gain a full outer shell of 2 electrons. So here is a basic ball and stick diagram for a covalent molecule. This one is methane. You have the carbon in the middle with the 4 hydrogens on the outside. It works because carbon has 4 electrons in its outer shell, so it needs 4, and these 4 hydrogens all provide it with 1, and each of the 4 carbon electrons go to form 4 covalent bonds represented by the lines. Again, we have to look at some limitations. What are the problems with them? What do they fail to show? So we're going to look at the limitations of the 2D model, which is the displayed formula, and the 3D model, which is our ball and stick model or diagram or whatever. So the limitations of this displayed formula is it doesn't show the 3D structure. It just kind of, shows how it's going to look. It doesn't show how it's all structured in 3D, which could be a problem when we come to giant covalent molecules. And it also kind of fails to show which atoms the electrons in the covalent bond have come from and how the electrons are shared, and unlike our dot and cross diagrams. And the limitations for this guy, our 3D model, our stick and ball model, ball and stick model, again, it doesn't show from which atom the electrons have come from, and it can also get confusing when we get onto the giant covalent molecules, where we have loads of different branches off. Each one will come off to 4 others. It can get really confusing really quickly. And finally, this is the molecular formula for hydrogen chloride. Molecular formula, it's almost the same as the empirical formula we talked about earlier. Remember, for GCSE, you need to know that the empirical formula, we reference that when we're talking about ionic compounds, and we reference the molecular formula when we're talking about covalent compounds and molecules. So now we're going to go on and look at the molecules, the substances formed from covalently bonded molecules. First of all, formed from single covalently bonded molecules. Water, for example, let's take water. So water is just lots of connected H2O covalently bonded molecules. So between our H2O molecules, we get this intermolecular force that holds them together, and that's what holds it into that liquid water. These intermolecular forces are weak because there's not really much to keep them together. In contrast, the shared pair of electrons between the hydrogen and oxygen cause strong electrostatic forces of attraction, which hold these two together, but we have these weak intermolecular forces holding the different molecules together. And following this rule, the melting and boiling points of these small covalent molecules substances are pretty low, because you only need to overcome that weak intermolecular force between the molecules to melt and boil them. You don't need to overcome the covalent bonds in substances made from small covalent molecules, which is why the boiling point of water is fairly low compared to a lot of other things. And the melting point is, well, it's liquid at room temperature, so we know the melting point is very low. And this is why most small molecular substances go round as liquids or gases. For example, oxygen and nitrogen in the air, they go round as gases because their boiling points are very, very low, and the minus temperatures, because their intermolecular forces between them are so very, very weak. And you don't have to overcome the strong electrostatic forces of attraction from that shared pair of electrons. You don't have to tear that apart to boil and melt small covalent molecules. Okay, a gap fill activity. The larger the small molecules that make up a substance, the small covalently bonded molecules, I mean, the higher the intermolecular forces between the molecules, or the stronger. So if you have very, very large molecules covalently bonded together, and then you have they make up these substances from small covalent molecules, the intermolecular forces are going to be slightly stronger, and this is more important when we come on to polymers. Take water. Water is a larger small molecule than oxygen is, isn't it? So the melting and boiling point of water are higher than the melting and boiling point of oxygen, and this is because the intermolecular forces between the molecules are slightly stronger because the actual molecules are slightly bigger. The substances made from small molecules do not conduct electricity because none of the atoms or molecules have any charge, and there's no free electrons, so there's nothing to pass the charge of electricity on, so therefore they cannot conduct electricity. So another molecule that can be formed through covalent bonding, there's the answer to question 2 here, are polymers. Polymers are just really long chains made up of lots of small units that are repeated over and over again because they're joined up. We look at this again more in paper 2 in organic chemistry. We look at how we form polymers through addition polymerization and condensation polymerization, but those are really not relevant to paper 1 at all, so don't worry about those until your paper 2 exam. So this is the displayed formula for a polymer. This is polyethene. You don't really need to know that. You're not going to really be asked the names. You just need to know that this is how we draw the displayed formula. These lines represent the covalent bonds. So these lines represent the fact that they join up to other units. Again, this unit is repeated over and over and over and over again to form these massive covalently bonded molecules. N represents that they are repeated for a certain number of times. So that just about answers questions 2 and 3. How high are the melting and boiling points of polymers? Well, let's think about how polymers are bonded. They're bonded covalently. Obviously, they're these big covalent structures, but polymers, they come together through the same intermolecular forces that substances of small covalent molecules are made up of to form like actual big ones. Because if you just had one polymer on its own, that would still be minuscule, probably too tiny to see. So you have lots of them joined together through intermolecular forces. But as we said, the larger the molecules that make up a substance, the higher the intermolecular forces between the molecules. The polymer molecules are very, very large, and this means that the intermolecular forces between two polymers, they are fairly strong. So we say that the melting and boiling points of polymers are fairly high. They're higher than the small covalent molecules, but they are still smaller than the ionic compounds that we talked about earlier, and the giant covalent structures, they're smaller than them. So giant covalent structures is simply where every single bond in the structure is covalent. So you get these giant chains of covalent bonds that could be huge. For example, diamond is a giant covalent structure, and graphite, we're going to look at those later because they're made from carbon. We have to go in a bit more detail. We've also got silicon dioxide, or silica, or what sand is made from. We're going to look at that in a minute. But the melting and boiling points of giant covalent structures are very, very high, because in giant covalent structures, when there's only covalent bonds, these covalent bonds have to be overcome, and these strong electrostatic forces of attraction have to be pulled apart, and yeah, this just makes the boiling points of them very, very high. So here is part of a silicon dioxide structure. Silicon dioxide, SiO2, that's its empirical formula. It's also known as silica or sand. So you imagine each grain of sand is entirely made up of covalently bonded silicon molecules in black and oxygen molecules in red. Each silicon bonds to 4 oxygens covalently, because the silicons are in group 4, so they have 4 electrons on their outer shell to share, similarly to carbon, whereas oxygen is in group 6, so it has 6 electrons, or it needs 2 electrons, and therefore each oxygen only makes 2 covalent bonds with each silicon, and this is how we get this tetrahedral kind of structure. I haven't always shown all 4 of the silicon's molecules, because it can get really confusing really quickly. Remember, that's a limitation of this 3D model. They will ask you for the limitations. We've gone over those. And finally, you need to be able to recognize the difference between substances made from small covalent molecules and giant covalent molecules. The similarity, obviously, is they're all made up of covalent bonds. The difference is that these small molecules, they're only like the small single covalent bonded molecules joined together by intermolecular forces, whereas the giant ones are all covalent bonds. They're all covalently bonded molecules, covalently bonded together, stretching out in massive chains and make different shaped structures. And polymers, they're kind of in between. You have repeated units of these covalently bonded molecules, but in the end, the polymer chains are bonded together through intermolecular forces. So we're pretty much out of the woods. We've covered the 2 hardest and most important, probably, topics of this video, but there's still quite a bit to cover, and it's still important to understand in chemistry, especially the states of matter bit, but also this metals bit. So if you want to pause the video and have a go at these 10 questions on metals. So how are metals bonded together? How does metallic bonding work? So when metals bond, what happens is they lose the electrons on their outer shell. So they usually have 1, 2, or 3, transition metals. It can vary. You'll learn more about that in A-level chemistry if you do it. But what happens is, it loses these electrons, and each metal atom forms a positive ion. But there's an attraction between the negatively charged electrons and the positively charged metal ions. So what happens is the metal ions, they come together in this tightly packed lattice structure with regular layers, and this kind of sea of delocalized electrons, we say, forms around it. So that just means that there's loads of free electrons moving around them, and that's how metals are bonding. It's the forces between the strong electrostatic forces of attraction between the positive metal ions and the negatively charged electrons that have been delocalized. We kind of call them this sea around them. I'll show you the model in a minute and you'll kind of get what I mean a bit better. But a delocalized electron is simply a electron that is not in the energy level of an atom, so it's kind of free to move. It's not like, hasn't got that force between itself and an atom necessarily. So this is the model that we use to show metallic bonding. At the start we have our metal atoms here, and these dots up here, these represent the electrons. Obviously different metals have different numbers, but they're usually low because metals have to lose electrons and form positive ions. That's what a metal is. But then once they're bonded, what happens is all of these electrons, they abandon their atoms. All the atoms form these positive metal ions as represented here, and then the grey represents all of these electrons kind of moving about in this sea of delocalized electrons is what we call it. You don't need to know any more than that for GCSE level chemistry. You should be familiar with the answer to question 4 by now. The boiling point of metals, again, very high. We see a lot of metals at, well, pretty much all metals at room temperature as solids because of this strong electrostatic force of attraction between the positive metal ions and the negatively charged electrons. And this really strong force has to be overcome to melt and boil metals, and this is why melting and boiling points are very high. It's also worth noting pure metals are very malleable, and that just means they can be bent easily and kind of worked with and modelled easily. And this is because the positive metal ions are arranged into regular layers. So yeah, as I talked about earlier, they come together into that tight lattice formation, but they're in regular layers, and this means that these layers can easily slide past each other, and it just means that the pure metal can be easily worked with. So metal alloys are simply a mixture of two metals, or a metal with a tiny bit of another element added in. Remember, different from an ionic compound, when the metal and the non-metal, there's a transfer of electrons and they bond. Metal alloys will be all or almost all metal, and if there's a non-metal involved, it will be there won't be much of it compared to the metal. And we need metal alloys because pure metals can sometimes be too bendy for their use. For example, I don't know, something like a spoon maybe. You don't want that spoon to be very easily bendable, otherwise everyone's going to bend it, and before you know it, it won't look like a spoon anymore. So we make these metal alloys, and these are harder than pure metals, and this is because, answer to question 8, they're harder than pure metals, and this is because the new metal or the new non-metal atoms, they distort the tightly packed regular layers of metal formed from metallic bonding, and this means that because they're not in regular layers anymore, don't really slide over each other that easily at all. They can't really be bent, and they're hard, solid, like pretty much every metal you will have come across and used in your everyday life. Finally, metals are good electrical conductors because the delocalized electrons are able to carry charge throughout the metal, and they're good thermal conductors. Again, we talk about conduction in physics when heat is passed on through kinetic energy and the vibrations of particles. In fact, we're going to be talking about vibrations of particles in a minute. But also the delocalized electrons, they can transfer energy as heat as well. So now we're going to move on to a study of the states of matter, because we've kind of been talking about melting and boiling a lot, but we really need to know the fundamentals about how that happens as well. Question 8 is for higher tier only, so pause the video and have a go. So here are the particle models for a solid, liquid and gas. You should be very familiar with these by now. The solids, they're packed together with strong forces between the molecules. Liquids, there's still forces between the molecules, but they're a lot weaker. The bonds between them are starting to break and they're coming apart, whereas gases, the bonds between them have broken. The forces are very weak and they're just moving around in straight lines, doing whatever. I should probably say, if I told you this was sodium chloride, so an ionic compound, what would the forces holding these two together be? Well, they would be electrostatic forces of attraction, because this would be a sodium ion, this would be a chlorine ion, this would be a chlorine ion, this would be a sodium ion, and these strong electrostatic forces of attraction would take lots of energy to overcome. If I told you this was ice, then what would the forces holding molecules together be? Intermolecular forces, remember, because each one of these would represent a molecule of H2O, but well, as we know, H2O as a solid is ice. The intermolecular forces between them, they're kind of enough to overcome the energy of the particles. So solids, they're the densest one, aren't they? They cannot be compressed. They're fixed, aren't they? They have a fixed shape, which is unlike liquids, which can flow and are less dense because there's less bonds between them. But liquids also cannot be compressed. Gases can be compressed, however. They're the least dense, and they're obviously constantly moving with random moving in straight lines kind of thing. Okay, so we have melting, boiling, condensing, and freezing to cover. We can kind of describe them all in terms of the energy and the forces between the particles. So, when a solid, let's take ice, when a solid is heated, the particles vibrate. The more it is heated, the more the particles vibrate, the more energy the particles have. As they vibrate, this weakens the forces between them, whether they be electrostatic or intermolecular, and at a certain point, enough of the bonds between them have been broken that the particles can come free from their fixed positions, and this is what forms a liquid. This is at a certain temperature. Remember, we call it the melting point. Then, as we continue heating our liquid, say water, the particles, again, more energy, they're moving more, they're moving faster, the bonds are breaking as the particles move, and at a certain point, all of the bonds between the particles will have broken. I should say, not the covalent bonds, if we're talking about simple molecular structures like water. Giant covalent structures, their covalent bonds have to break because there's no other bonds, but simple molecular structures, as we covered earlier, it's only the intermolecular forces. So with water, all of the intermolecular forces will have been overcome by the vibrations and energy of the particles, and all of the individual particles will be free to move around, and this is a gas, and this happens at the certain temperature we call the boiling point. We look at this in a bit more depth in physics and latent heat and all that. But at condensing, when we cool a solid down, the particles or the molecules, they stop moving quite as fast, they start to slow down. The forces of attraction between the particles kind of pull them together a bit, bonds start to form, and at the boiling point, remember, we don't call it the condensing point, it's still the boiling point, even if it's condensing, because it is the same point, so we don't need two different names for the same point. So many bonds have formed as the molecules have cooled down and stopped vibrating, so many bonds have formed that they're all back down to Earth in a liquid, and then as this liquid continues to cool, we head towards the freezing point as more and more bonds form between the molecules as they lose less energy, and the forces of attraction between the molecules pull them together even more. Eventually it becomes a solid as the particles lose all their energy. The positions of the molecules become fixed as we know solids are. They have fixed positions, all the molecules. And in solids, there's not enough energy to overcome the attraction between the particles. And that is a basic tour of how we go from a solid to a liquid to a gas and back to a liquid back to a solid. We can go straight to a gas sometimes. This is called sublimation, but it's not in the chemistry specification, and I haven't checked the physics specification, but even if it is in there, you really don't need to know much about it. If you want to, just remember it's called sublimation, 1 mark at the most. I doubt it'll come up at all. Okay, so this question here, it could be like one of those exam questions that's worded trickily. The amount of energy needed for a substance to change state simply depends on the strength of the bonds between the molecules, and obviously the strength of the bonds between the molecules, it depends on how they're bonded, first of all, if they're ionic, and if they're ionic or covalent, so if it's electrostatic forces holding the molecule together, or if it's simply weak intermolecular forces. Also, another thing to remember, we talked about this when we talked about polymers, I think, the size of the particles. The bigger the particles are, bigger particles have stronger forces of attraction between them. And coming on to question 8, this could actually be used to answer question 8. One of the biggest limitations of the particle model is it doesn't show the type of forces holding the molecules together, so we have no way of knowing how strong the forces of the particular solids shown in the model, how strong those forces are. Also, the particles are drawn as spherical, solid, and inelastic. In reality, they are none of those things. Now we're going to introduce something that's very important with chemical equations that we're going to look at more in the 4th topic. The state symbols. You need to be aware of the 4 state symbols, and you need to be able to put them on all of the equations that we cover in chemistry. So there's 3 states of matter, obviously, solid, liquid, gas, but we know there's more, okay, plasma, there's other ones, but you need to know at GCSE level there's 3 states of matter, solid, liquid, and gas, and I'll show you how we symbolize this, but there is a 4th state symbol, aqueous, and aqueous simply means dissolved in water. So if we have a solute that's dissolved in water, then we'll describe, and it's in a chemical reaction, then we describe that as aqueous. So here are some examples quickly. We got sodium chloride, one of our most basic ionic compounds, solid, S, H2O, water, L, liquid, oxygen, O2 is a gas, G, and hydrochloric acid. Often we'll use dilute hydrochloric acid, which basically means we've mixed hydrochloric acid and water, so that it's kind of dissolved in it, so we call it aqueous, and we put AQ, remember we put them in brackets down at the bottom in subscript, like the small 2. Make sure you do that, they're really picky. Those examiners are really picky on their formatting, so make sure you get all your formatting for the chemical equations correct. Now we are going to go and have a look at carbon allotropes. So what is an allotrope? It's simply a different form of the same element. So for example, graphite and diamond are both entirely made out of carbon, but they're different forms, they have different structures. So the carbon allotropes that we're looking at, they are giant covalent structures. So they are entirely made up of carbon atoms covalently bonded together. So first of all, we're going to look at diamond. So we have diamond here in the top left. As you can see, each carbon atom is bonded to 4 other carbon atoms. So it makes, because each carbon atom has 4 electrons on its outer shell, so it makes 4 covalent bonds. Diamond will have a high boiling point because of obviously the covalent bonds have to be broken, and that requires lots and lots of energy. They are not conductive as there's no delocalized electrons to carry charge or ions to carry charge, and it's very hard, again, because these strong covalent bonds hold each carbon atom in a fixed position. So graphite is made up of hexagonal layers. Graphite is here on the top right, As you can see, each carbon atom is bonded to 3 other carbon atoms this time, and it makes these layers. What this means is each carbon atom has a 4th electron that is delocalized in between the 2 layers. So, like diamond, high boiling point, hard, it has to be noted because they're layers, they can slide over each other. So you imagine graphite is used in pencils, so when you're drawing, you imagine those layers of graphite sliding over one another as some put on the page, whereas others stay in the pencil. But then conductivity is different because graphite has these delocalized electrons in between its layers, so graphite is in fact electrically and thermally conductive. Graphene is simply a single layer of graphite. Once again, graphene, high boiling point, it's strong but also light. Again, it contains delocalized electrons because, as we can see, each carbon atom is bonded to 3 others, so there's going to be 1 free electron. And graphene, because it's only a single layer of atoms, it can actually be used for in specific scientific things. It can be like added to composite materials, for example, and it's also used in electronics as it's very small, and as I said, it's conductive because it's got those delocalized electrons to carry charge. So fullerenes are simply carbon allotropes that have a hollow shape. So the structure of fullerenes, they're predominantly made up of hexagons. So down here at the bottom, these are 2 fullerenes. You can see they're predominantly made up of hexagons, but they can contain pentagons and heptagons, so 5 and 7 sided shapes within them. But that's generally how the structure of fullerenes are right there. The first fullerene discovered was Buckminster fullerene. That is this ball here. This is a Buckminster fullerene, C60, 60 carbon atoms bonded in each Buckminster fullerene sphere. And finally, carbon nanotubes have a very high length to diameter ratio. As you can see, they're only 1 atom thick. This can make for them being used in some kind of very exciting areas in chemistry. So carbon nanotubes, they can conduct electricity because obviously in the carbon hexagons there's going to be a delocalized electron. These are also very, very strong. And finally, what are fullerenes used for? Well, they can be used as catalysts, for example, or lubricants. They could be used to deliver drugs into the body as they're very, very small. Again, they can be used in electronics because they conduct electricity like graphene, and we also use them in nanotechnology, which we're going to cover in now. So we're going to whiz through some stuff on nanoparticles. It's only coming up in the Triple Science Foundation exam. It's the only bit of the entire chemistry course taken out of the chemistry paper 1 exam for Triple Science Higher, and this was never ever in combined science exams. You never have to worry about it if you're doing combined science. So pause the video, have a go at these 9 questions. Coarse particles, also known as dust, they are between 2,500 nanometers and 10,000 nanometers large. Remember, nanometers are very, very small. 1,000 millimeters in a meter, 1,000 micrometers in 1 millimeter, 1,000 nanometers in 1 micrometer. So 10,000 nanometers is 10 micrometers, 0.01 millimeters. So that's very small, isn't it? How big are fine particles? Fine particles are a step down from coarse particles. They are between 100 nanometers and 2,500 nanometers, so getting even smaller. And finally, nanoparticles are particles that are below 100 nanometers in diameter. They will only ever contain a few hundred atoms. They're very, 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 very tiny. So because they're so tiny, they're going to have a high surface area to volume ratio, and this is important. You might be asked about this. So to calculate the surface area to volume ratio, you do the surface area divided by the volume. You also need to know the relationship between the side length of a cube and its surface area to volume ratio. So as we decrease the side length of a cube, its surface area, by a factor of 10, its surface area to volume ratio increases by a factor of 10. That's something you need to know. And that's why nanoparticles, because we shrink their diameter really, 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 really small, its surface area to volume ratio gets really, 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 really big. And this incredibly high surface area to volume ratio means that nanoparticles have sometimes have different properties to the regular molecules that we use, and it also means that we'll often need less of a material that's made up of nanoparticles than you would a material made up of normal molecules because of that really high surface area to volume ratio. So nanoparticles have many, many applications. They can be used in medicine to deliver drugs. They can be used because they're electrically conductive, as we talked about over here. They can be used in tiny electrical components. They can be used as cosmetics and sun creams. They can be used as deodorants, and they can be used as catalysts. So the advantages of using nanoparticles, because they have this really, really high surface area to volume ratio, they're going to make really effective catalysts. Because they're really, really small, they can deliver drugs better than any other technology we have. Again, because they're really, really, really small, we can build tiny, tiny electric circuits, and this can just make computers and computer chips more compact. We can use them in cosmetics and like moisturizers and lubricants because they slide really well. We can use them in sun creams as they're better at protecting your skin from UV rays than normal sun creams. But there are, as with anything, the risks of using nanoparticles. They are a relatively new technology, so we do not know the long-term impacts they will have on human health, which is kind of problematic considering we're using them already in medicine. But we don't know the long-term. We don't know what long-term impacts they may have. We really should test the new products, otherwise, because we don't understand how they affect the body, basically, because they're really, really small. We don't understand what's going to happen. They could damage cells. They could cause cancer. We don't know. There's no evidence so far to suggest they do, but long-term impacts we still don't know. That only comes with time. And there's also the possibility that if they can get washed away into the environment, and like microplastics, they can really damage the environment, because you imagine a world polluted by nanoparticles. These like hundreds of titanium dioxide atoms grouped together. You won't be able to see them, but they'll just be there like a harmful pollutant. We don't know. Essentially, the risks of using nanoparticles, basically, we don't know enough about them. So we've finally made it to the end of everything bonding related. It's a massive topic, I know, and a complicated topic, lots to get your head around, but if you've got your head around everything in this video, I can guarantee you a high grade in chemistry. Again, come back and revise it so that everything sticks in your head. Practice, for example, empirical formulas, figuring out what magnesium bromide looks like as an empirical formula, for example. Practice, practice, practice. Go and look up some exam questions on bonding, see how it comes up, usually, to make sure you're fully prepared to tackle the unknown compounds they're going to throw at you in the exam. So just as a quick recap, here's the ionic bonding questions, the covalent bonding questions, the metallic bonding questions, and the states of matter questions. and finally the allotropes of carbon and questions on nanoparticles, these nanoparticles only for Triple Science Foundation. If this was helpful, please consider subscribing and share so that other people can understand chemistry and be able to get better grades in their chemistry exam. And yeah, I hope you now have a better understanding of the world of chemistry.